Okay, part two of the control theory uh, series. I thought I'd show you how we're going to actually implement this in code. And so if we come to our VS Code environment, um, we are in the launcher subsystem, and we have, for our launcher subsystem, we have three motor controllers. We have a launcher lead and follow, and a pivoting hood. And we need to have three motor controllers because in this subsystem we have three motors. The launcher itself is controlled by two motors which are tied together with a gearbox, and so we have a lead and a follow so that the motors don't clash and interfere with each other. They spin at the same rate. And then we also have our pivoting hood motor, which through the pulley and gearbox pivots our hood. And as well, there's the sensor here, and there's the pulley kind of, and it's also kind of cool because there's a bearing here which allows it to be on the same shaft as a shooter but spin at a different rate. So if we look at our VS Code, there's these values here, which are parameters that we will need to tune based on our system. We'll need to make sure that the sensor phase is true, meaning that a positive voltage results in a positive change in an encoder value, and a negative voltage results in a negative change in encoder value. You don't want to give it if you're trying to get to a certain set point and you say move forward and it goes backwards, then you'll never achieve your desired target. So we need to make sure that our sensor phase is correct. And then there's these P, I, D, and F values, which we will need to tune based on our system so that we can use motion magic mode. And the way that we're going to tune these values is through this nice method called tune launcher, which Cross the Road Electronics has provided for us, and we have ported over into our code so that we can use it. The tune launcher system basically allows us to use our joystick to control the motor, and then it has it has a string builder. So basically it's going to output some signal through a console so that we can read it. And then as we look through here, if a button is pushed, it goes into velocity closed loop mode. Otherwise, so if the joystick button is pushed, it does all of this. Otherwise, it just sets it to percent output. So like full throttle on the joystick means full throttle for the motor. So what we'll do is not push the button at first, ramp it up to full throttle so that we can measure the output. And based on that output that's given, we can then assign an F value. Right here, what we did was we just took the F value from the launcher motor and copied it as a placeholder. But if we think about the F value as what's called the feed forward, and basically relating the motor voltage to encoder velocity, because we have vastly different gear ratios here. Here we have about a 3.5 to 1, and here we'll have over 100 to 1. That's because we want the shooter wheels to spin really fast, and we want the hood to be much more controlled and spin very slow. So the F values will be vastly different for our hood than it will be for our shooter motor. So anyways, we'll tune these values based on the output. And then we will push the button, and it will achieve a desired set point using the encoder as feedback to actually achieve a target velocity. And that will then allow us to then compensate for any small errors with P, I, and D. Most of the time, feed forward looks pretty good and will only have a P value to correct for any additional errors. In some circumstances, we may have an I or a D. The I value will help compensate for steady state errors that may occur. If we look back here, if we never actually get to our target value, we can add a little bit of I to add up the error over time so that it gets to where it's supposed to go. Let's see, what else is there? And then that's how we're going to tune our system using WPI Live and Crossroad Electronics libraries. Cool.